are these three vectors a basis for R3? Are they a basis for R3? So, oops, basis, no, is. Okay, so I can see that if I put them in a matrix, I have a pivot every column, so they're linearly independent. I have a pivot every row, so it spans all of R3. So yes, so because a pivot every row, that means it spans R3. And I have a pivot every column. So that means they're linearly independent. So therefore, yes, a basis for all of R3. Okay, so looking at these three vectors, well, here I have the 0 vector. And when there's a 0 vector, that means they are not linearly independent. So not linearly independent, so not a basis. So basis is a linearly independent spanning set. Here I have 4 vectors with 3 entries. So this is not linearly independent because I have more vectors than entries. So not a basis. Here I have 2 vectors. So even if I don't even need to go further, when I put this together in a matrix, can you see I cannot get a pivot in every row? That means I cannot span R3, so not a basis for R3. Okay, and you should just know this, the wording, this is called the standard basis for R3, this is called the standard basis for R4, and you're pretty familiar with those vectors. All right, so let's look at this. So here I have 1, 2, 3, 4, 5 vectors in R4. So in and of themselves, these 5 cannot be a basis, but they're saying find a basis. So this is where we're going to use our efficient or spanning set theorem. Let me come back to it. We're going to use this spanning set theorem, and we're going to find out which vectors are related to each other. We'll get rid of it, and we'll remove, we'll remove one, and then we'll find a set that spans the set, and we'll be able to make it linearly independent. So let me take some time now and put it on my calculator. Okay, so I've entered these vectors into my calculator, and I reduced it to get to this. So what I'm going to do is I'm going to pick out the pivot columns, right? So first I go to the pivots by coming in the pivot rows. Right, there's a pivot, and then there's a pivot. Okay, so those are the 4 pivots, and their entry are 4, so that's good. So I have 4, so it's going to, whatever vectors I pick, it's going to be a spanning set. So I want to pick 1, 2, 4, and 5. So a basis for the subspace spanned by this will be these vectors. So 1, 0, negative 2, 3. Oops, I meant to write. So I need to list the vectors, right? Comma, 0, 1, 2, 3, comma, 2, negative 1, 10, 3, and the last one, 3, negative 1, negative 6, 9. So these 4 vectors are a basis. I've taken out the one vector that was linearly dependent. So this is an efficient spanning set. It's linearly independent, and it spans the area, or I guess this one actually spans all of our 4. But all I needed to know was it spans this subspace. All right, so I've got these 3 vectors. Okay, they're telling me there is a relationship between the 3 of them. So it's like they're all related in this way. So if you put them all together, Maybe there's just 3 little boys who play in the neighborhood. You put them all together, it's not a good thing. It's a 0. So what I need to do is I need to take one of them out. It doesn't matter which one. As soon as I take one of them out, this relationship doesn't stand. So then it makes them linearly independent. So a basis, yeah, sorry. Write that again. So a basis for H will be any two of these 3 vectors. So I could choose this, or I could choose this. So it's not unique what the basis is. As long as they're not dependent, then they span the same set. Well, I'm taking back what I said. I thought I would verify it on my calculator. So I put these 3 into my calculator and row reduced, and I got that. So I cannot choose these last 2. So there is some kind of relationship between these last 2. So I really do need to make a linearly independent set. So I really do need the first 2 vectors. So knowing there's a relationship between them is a starting point, but do put it into your reduced row echelon so that you can find the pivot columns, which shows they're linearly independent. So I need the first 2 vectors to make a basis for this space. Okay, so looking at this matrix A, and here's a V1 and here's a V2. So what they're telling us is there is an X in the domain that gets to the V. I'm sorry, it should be a W, right? Yep, okay. There is an X in the domain, right? There is an X here that gets to the W in the codomain. And there's another X, right? Doesn't say it has to be the same one. There is another X that gets to V. Oops, sorry, I said that backwards, but we get to 2 different vectors here. Okay, and we know it's consistent, so solutions exist. So there is an X, right? Okay, so do I know that V plus W is in column A? Okay, so let's see, remember what we know about column A. So column A is the range of the transformation, right? Column A is the linear combinations of the columns of A, right? The linear combinations of the columns of A. And don't we know that column A is a subspace? And if it's a subspace, if I take any 2 items in my subspace, meaning V plus W, it has to be closed under addition, right? So if I take a V in column A and I take a W in column A and I add them together, it has to stay in column A. So the subspace column A must be closed under addition. So yes, V plus W is in column A. Column A, I meant to say.